Welcome.
Okay. Thank you, Jose. Thanks for introducing me. I'd also like to introduce the other two co-authors of this paper. One is Allan Strong, the program director, and the other is Steve Phillips. Both are available for questions on this topic if you need to ask them outside the QA session. So, as a note, I'll be referring to Rainbow Falls as RF from now on because Rainbow Falls is a mouthful. So, background-wise, Sun introduced the CMT concept in 2005 with Niagara, which was branded as UltraSpark T1. This was followed in quick succession by UltraSpark T2 and UltraSpark T2 Plus, and finally RF, which is 16 cores in a chip. It's an industry first. So what is the progression of thread count across the 4 generations of CMT chips from Sun? Niagara was implemented with 32 threads. This was followed by T2 with 64 threads. T2 Plus was implemented with 128 threads in two-way mode, or 256 threads in four-way mode. And finally, Rainbow Falls, or RF, implements it as 256 threads in two-way, or 512 threads in four-way. So once again, I'd like to emphasize that RF is the first in implementing 16 cores in a chip, and it's not really for advertising purposes, but just emphasize that this was a significant design challenge. Aside from enhancing the thread count by adding more cores, we've also gone ahead and refined the CMT concept by providing or extending glueless node-to-node coherent interconnect to four-way, meaning no coherent hub is required for node-to-node connectivity. I'd also like to mention some of the other generational improvements that have been implemented in order to support, say, either keep with the industry standard or support the greater number of threads on our chip. One example is PCIe Gen 2.0. We've enhanced the I/O networking by implementing Gen 2.0 speeds. Within the core, we've implemented certain ISA extensions, for example, fuse mul add in the floating point to enhance floating point performance. You may have attended an earlier talk by Lawrence Spracklin on hardware accelerators, crypto hardware accelerators. That too has been significantly enhanced, providing user-land non-privileged access to an otherwise hypervisor accessible, only accessible hardware accelerator, hashes, etc. However, I will not dwell on this particular topic. It won't be an overview. Instead, I will focus specifically on the challenges that we as a design team faced in integrating 16 cores on a chip, and also in supporting the related bandwidth requirements of 128 threads on a chip. Now, one may think that this is a mundane topic to cover, but in fact, especially given that Sun has become an expert in this with 3 chips prior to this, but integrating 16 cores is another dimension to the chip design, and we had to iterate multiple times between architecture and integration to come up with an architectural spec that could be implemented in the least invasive way possible. So this is where I take out my laser pointer. So this is a picture which I titled as massive data flow across the hierarchy, which is somewhat of an understatement. So I've simplified this logic diagram. It's really, what it shows is the 16 cores, which we've doubled, interfacing to 16 L2 tags. So the L2 cache in RF has been sized up, and we've also increased the number of banks, doubled the number of banks over the prior generation to provide more bandwidth, simultaneous bandwidth into the tags in the L2 cache. So the fact that we support 16 cores over here ripples through the entire design hierarchy all the way out to, say, the pins. So the coherency unit, which processes remote accesses to memory on remote nodes in the system, or to local memory, has also been upsized to support a new bandwidth spec. So in ensuing pages, what I will do is I'm going to focus on this area, which is the core crossbar L2 tag complex, and then this particular area, which is the coherency unit accompanied by its own ingress queuing crossbar and link frames along with coherency units, coherency links which interface to remote nodes. And prior to entering this, well, so before I talk about the challenges, what I'd like to emphasize is the goals that we set out for ourselves. We had to, number one goal was limiting the impact of adding all these threads, whether it's the cost in area, power, etc. Number two was to also compensate wherever we can, because we had significant resources to support all these threads, but then there are areas where we could afford to say, reduce in terms of area impact or other related costs to compensate. And the third is enhancements. Yeah, we add a lot of CMT threading related features, but we're trying to make it more easy for, say, our partners, such as system partners, to go ahead and integrate it. I'll give you some examples of how we make their task easier. So challenge-wise, I'll go through this briefly. So on-chip connectivity is one. We have massive buses throughout, and that's just a fact given that we support 128 threads. Some of the areas where we have these massive buses focused are the 16 cores interfacing to 16 L2 banks. The other area, again, which I had shown to you on the slide, was the coherence units interfacing to link framing units and then on to coherency links. In each case, you'll see hardware resources being thrown at it in order to support the additional bandwidth requirements, but in a manageable way. The other thing is reducing interface count. So unfortunately, most of our interfaces tend to be quite wide because we push-pull data across it, whether it's through the L1 caches or the L2 caches or the memory or remote access. So we made multiple trade-offs in this area of reducing the interface count. Again, we focused on that particular complex of core versus L2 banks. And then to compensate, we've gone ahead and reduced area of certain larger components. One example being the L2 tags, where we've gone ahead and merged it in the high-end part of the pipeline, which is responsible for miss processing or fill processing or snoop processing. We've combined functionality and buffers, etc. Also converted the directory from a CAM to an SRAM. I'll explain more about this later. And I've also mentioned more than once about the demands of the 4 coherency units, so I'm going to skip this bullet. And then there's chip-to-chip connectivity. That was also high on our priority list to optimize the feature set available to, say, our system partners. And we've done it through a couple of means, which I'll talk about later on. Okay? So this is a floor plan of RF, and this is the tape-out floor plan. I provided this instead of a layout view because then you can go ahead and see exactly what we've done in terms of placement of critical clusters. So our floor plan is really crossbar, core, L2 cache centric. This is the crossbar. These are 8 Spark cores on top, on bottom, interfacing. The interface is to and from the crossbar for both the L2 cache array and the Spark core. we've kept the path length from the Spark cores to the L2 cache as short as possible. Okay, so everything else is effectively arrayed around it, but in a symmetrical manner, because typically we have a power of 2 number in clusters. I/O is also very high in count because we support 6 coherency unit links, multiple memory channels. So there's a symmetric distribution of the links around the chip. So now focusing on the challenges and providing you a little more detail. So spoken time and time again about the crossbar and how critical that is to converging on the chip. So there are certain design constraints that are invariable because, for example, our core request paths are wide. Okay, there's no way we can compromise around that. Now, if we had a fully connected CCX, we'd actually have 16 request ports and 16 response ports coming in and going out of that. We don't have the tracks to support that, nor do we have the area to support that, nor can we burn all that power. The statement here is that fully sizing this makes CCX unroutable within the allocated area. So that is true, and we've addressed this up front. So the solution here is, given the problem statement in the prior slide, is we paired up, say, cores, and we paired up L2 banks. So if you remember from the prior slide, well, there's a slide after this where I can show that to you. But cores have been paired up. They interface to this crossbar through a common port. This way we have 8 interfaces into the cores. And then similarly, the L2 tags, the 16 have been paired up. And they have each pair has a common interface to the crossbar. What this also means is that given that we've limited access somewhat into the crossbar, we also have to supply high bandwidth elsewhere, say through the L2 tags. Otherwise, we'll have stalls on the crossbar. So the banking and the L2 tags helps us to some extent in that. So as a consequence, we have an 8x9 CCX with compact dimensions operating at the highest chip frequency, which is quite amazing given that it's wire dominated and wires typically don't scale with the frequency or process. So here's a logical diagram of the arrangement of Spark cores, L2 tags, and then the crossbar. This somewhat reflects how we also floor planned it. If you remember the floor plan with the Spark cores on the top and bottom, and then the CCX in the middle. This also shows how we've gone ahead and done the merging of L2T, sharing 2 data pipelines, and then also the gasket, which is shared by 2 Spark cores and accessing the CCX. So coherence unit to link connectivity, that was another significant challenge for us because there are higher bandwidth requirements in this generation for coherent accesses, whether it's remote or local. So I'll go ahead and skip the second and third bullet over here and go directly to, say, the issue at hand, which is that we have to keep some number of virtual channels independent, which leads to this uptick in SRAMs and queuing requirements over here, 18 total queues, each up to 128 entries deep. We have 2 coherence planes, which means we need to support 2 such large sets of queues. So we also have, on top of that, total number of outstanding transactions are up to 1,024. How does one limit the impact of fully sized queuing and guarantee functional correctness with undersized queuing? Our solution over here is to introduce flow control across the coherence links. So Sender and receiver, they both have credits. Sender has a credit amount, and then receiver releases the credits back to it over a transactional link message. This avoids the need to fully size queues, reducing area requirements. The other significant benefit is that if we didn't have something like this, we would have to verify the functionality in a multi-node test bench. Simulation times are very slow, uncovering corner cases is very slow, etc. We've simplified the problem here by just having to simplify it, making it a more limited problem, and just verifying the flow control instead, aside from other test cases. But the problem is more bounded here. So this is a picture of what I've been talking about, the two coherence planes, coherence units. There is a fan out into the links. There's no queuing on the egress side. There is queuing on the way back, and then you can see the array of 18 queues, which have to be kept independent for functional reasons. However, they are no longer fully sized, and this is the problem we focused on in this particular arena. So reducing area of larger components, this is just one example. I'm not going to dwell too much on this particular slide over here. And then there's chip-to-chip connectivity. So we've done better than the prior generation in terms of multi-node connectivity by removing the need for, say, a coherence hub leading to a hop between nodes. That also complicates the system design in some sense because these particular traces on the board have to be kept to within a certain limit. And we also have more links in general in the system associated with the chips than the prior generation. So we've gone ahead and proactively come up with certain solutions over here. One is the ability to mirror a coherence plane, and the other is the ability to configure your link mapping. So logical links can be mapped into any set of any one of the physical links within a coherence plane. So there's a great advantage to this because typically chip design precedes system level design, and by months, if not up to a year. So having proactively put in this facility and providing maximum configurability, we've addressed this upfront instead of having to complicate the system design unnecessarily. So here's an example. Now, this is really an ideal case. Nobody would actually implement a system in this manner. But what I'm trying to do here is just show you the fact that we can accomplish a case of complete non-overlap on the links between a chip. So node 0 has coherence plane 0, coherence plane 1. Node 1 has coherence plane 1 flipped with coherence plane 0, such that they're actually adjacent to each other. Okay? So as a consequence, for this particular case, we don't have to overlap routes now. Yeah, there are multiple levels of routing within a board, but we tried our best to avoid any of that by providing this configuration. But on top of that, what we also have is, say, the ability to map a logical link onto any of the physical links within a coherence plane. So for example, if you see this is physical logical link 0 mapped on to, say, physical link 0. But in this particular case, what we've done is we've gone ahead and swapped the mapping, so you avoid the overlap over here. So before I go ahead and summarize, just like to make a few comments about the status of the chip. Silicon was available in June. It's doing very well in the lab. It's meeting or exceeding expectations, and looking forward to systems based on this. But we seem to be going well here in this particular area. So summary, RF had a series of challenges that it needed to meet, and the challenges were mainly focused around supporting the 16 cores and then all of the data flow associated with that and the bandwidth requirements. Our goal was to minimize the impact, which we've done pretty successfully over here. So I think I'd like to go ahead and end this presentation over here. And if you have any questions, I would like them to be limited to the scope of this presentation, but still try questions even if they're out of that. We'll see if we can answer it for you. There are some constraints on what we can say.
One question I have, I didn't see from your talk. There was a, did you increase the bandwidth in order to adjust for the scalability of your system? Did you change the coherence? The
protocol?
The protocol that you have? Or is
No,
it the same as the previous generation?
The protocol was more or less the same.
Okay.
Yeah.
Allan Baum, Intel. Two questions. The physical interface between the two chips, what is that based on?
It's a SerDes interface.
How wide? How fast? Can't say. Okay.
Can't say, but perhaps I can. So 14-bit wide. Okay, and there are 6 of them.
Okay, and the second question, you talk about 2 coherence planes. Are those just address striped?
Yes. Yes.
Okay. Thanks.
Mariama from Fujitsu. I have a question about your L2 cache structure. You have mentioned that the L2 cache is divided into 16 banks. And can you mention about the associativity of each bank?
The associativity, if I'm not mistaken, is 16-way. Okay, but
so I think that each bank has like a 16-way. Is that what you're saying?
Yes.
Wow. Thank you.
Okay. Is that it for questions? Okay.
There is no more questions. Let's start the speaker. Give it to him. Now we're going to have 2 talks about the IBM Power 7. The first one is about the processor side. The next one is going to be about the system. The first speaker is going to be Kalla. He's been at IBM, and he's working on processors over 26 years, and he's in some systems like the IBM S370, Motorola 68000. He has several patents, of course, and he's a master of invention from IBM, master inventor at IBM.
Okay, thank you, Jose. Okay. Hi, today I'm going to be unveiling the Power 7 processor chip and sharing some microarchitectural details with you. Before I do, I'll spend a few minutes on the history of the Power architecture. Then I'll talk a little bit about the motivation and the principles for the Power 7 design. I'll give you an overview of the chip and some of the microarchitectural details. And finally, I'll wrap up with some status on where we are in the design cycle. IBM has been doing power processor chips for just about 20 years now. We introduced our first power processor in 1990 using the America's chipset. Along the way, we have incorporated IP from our highly reliable I-series processors and performance features from our 600 series workstation processors. As you can see from the chart, IBM has consistently introduced new generations of the power processor every 3 years. There have also been many plus versions not shown on the chart between generations to leverage new silicon technology. Along the way, IBM has led the industry, delivering to market many new innovations such as RISC architecture, out-of-order execution, hardware multi-threading, which was actually introduced in hot chips in 1997, dual-core processor designs with the Power 4 chip, simultaneous multi-threading, which I had the pleasure of introducing here at Hot Chips in 2003. Today, we are introducing our 7th generation processor, continuing IBM's tradition of innovation, introducing a balanced 8-core multi-chip design, embedded DRAM, and 4-way simultaneous multi-threading. Okay, here's a die photo of the Power 7 chip. Power 7 is fabricated in IBM's 45 nanometer silicon on insulator technology using copper interconnect and embedded DRAM for the L3. The chip is 567 millimeters squared and contains 1.2 billion actual transistors. However, if you consider that each EDRAM cell on the chip is actually the equivalent function of a 6-transistor SRAM chip, the chip actually has the equivalent of 2.7 billion transistors. Having the L3 on chip has multiple advantages. There you can see the L3. The biggest advantage of bringing the L3 on chip is the latency reduction. Eliminating driver and receiver delays, the L3 on the Power 7 chip can be accessed in as little as 1/6 the number of cycles of the previous generation part. Second is improved bandwidth to the L3. Using on-chip interconnect with 11 layers of metals, we can run 32-byte buses to and from each core, providing twice the bandwidth per core of the previous generation. Less power, the EDRAM uses about 1/5 of standby power of a traditional SRAM cell. EDRAM is also 1/3 the area of SRAM cells. The large EDRAM L3 also acts as a filter, reducing the per-core traffic to the memory controller and SMP interconnect. The chip, as you can see, has 8 processor cores, each with 12 execution units, capable of running 4-way simultaneous multi-threading, providing 32 threads per chip. To feed the 8 processor cores, we have 2 memory controllers on each side, one on each side of the chip. Each memory controller supports 4 channels of DDR3 memory. Combined, the 8 channels of DDR3 memory provide 100 gigabytes per second of sustained memory bandwidth. And that's not peak, that's sustained. On the top and bottom of the chip are our SMP links providing 360 gigabytes per second of coherency bandwidth to make SMP systems scale to 32 sockets. Okay, let's talk for a moment on the design principles for the Power 7 chip. The most important aspect in designing an 8-core part was to have a balanced design, making improvements in performance, scalability, energy efficiency, and RAS. We didn't want to simply put 8 cores down on a piece of silicon with a mux to memory and call it an 8-core chip. Doing so would provide great single-threaded performance, but would fall off rapidly when you start scaling up. So in designing the Power 7, we took a different look at performance. Compared to the traditional performance graph at the top, the graph at the bottom has single-threaded performance on the x-axis and throughput on the y-axis. The idea being is you scale up from thread, core, socket, and system. You want to see a steep curve maintaining high levels of thread performance. We also wanted to shift the curve from our previous generation Power 6 to the right, providing performance gains at all levels for a balanced design. Thread level performance is increased dramatically by sharing core resources like caches, TLBs, and register renames, such that in a single threaded mode, all resources may be used by one thread. Also, for single threaded workloads, the entire 32 megabyte shared L3 is available. Core level performance is improved by adding 4-way simultaneous multi-threading and aggressive out-of-order execution. This enables Power 7 to provide increased core performance from Power 6 with a smaller, more energy efficient core. We'll talk more about core performance later. At the socket and system level, Advances in cache hierarchy, memory bandwidth, interconnect technology, and coherence protocol allow us to transition from a 2-core chip to an 8-core chip and still maintain the balance of memory and SNOOP bandwidth per core of our previous generation. This is crucial in building large-scale systems. In the next presentation, Bill Starke will explain the details on how this was accomplished. Another important aspect of the Power 7 design was to provide customer flexibility and adaptability. The Power 7 design and packaging options allow Power 7 chips to be used from single-socket blades up to high-end 32-socket servers. Also, it's used for huge petascale clustered systems. Although the base chip is an 8-core design, we'll be offering 6- and 4-core versions of the chip. This allows IBM to offer different performance levels for systems based on core count, along with traditional frequency binning. Each core also has its own digital PLL, allowing independent frequency control per core to match workload demands. To balance workload threading requirements, the Power 7 chip can switch between SMT1, SMT2, and SMT4 mode dynamically. Currently, 3 packages are being offered for the chip. A low-end organic package with 1 memory controller and 3 4-byte links for systems up to 4 sockets, a high-end ceramic package bringing out both memory controllers and 5 8-byte SMP links for up to 32-socket systems, and a compute-intensive package offering 32 cores per socket with doubled-up internal buses for high-performance computing applications. With the 4 Power 7 processor chips, this socket is actually capable of 400 gigabytes per second of memory bandwidth that's sustained for extreme computing applications. Okay, let's take a look at the Power 7 core in a little more detail. If you look at the core, you can see in the center of the chip, you can see the 2 fixed point units. Those are aligned directly above the 2 load store unit pipes on the kind of the left side of the load store unit. The idea being is we want those buses engineered directly to the load store unit. The second level translation is to the right of the load store unit. Also in Power 7, we've increased the flexibility of the load store unit by having it being capable of actually executing fixed point instructions also using the AGEN part of the pipeline. On the upper right there, you can see the 4 merged vector and scalar floating point pipes capable of 4 double precision multiply add operations per cycle, or 8 flops per cycle per core. Multiply that times 8 and you got 64 flops per cycle. The instruction fetch unit, which also contains the condition register execution unit and the branch execution unit. The instruction fetch unit also contains our branch prediction logics, which we have improved in Power 7 to provide greater performance per core. Let's see, got it? Oh. There we go, sorry. On the top of the chip is our decimal floating point unit, which we introduced in Power 6 to accelerate commercial applications. The instruction sequencing unit has been made more flexible in Power 7. The instruction sequencing unit is now capable of dispatching 6 instructions per cycle, including 2 branches per cycle. The instruction sequencing unit also can issue 8 instructions per cycle to the 12 execution units. In Power 7, we took advantage of the out-of-order execution to switch from a dedicated recovery unit to a distributed one using the branch and redirect capability of the out-of-order machine. Looking at the cache hierarchy, you can see the 32K byte I cache in the instruction fetch unit, the 32K byte data cache in the load store unit, each being serviced by a tightly coupled 256K byte L2 cache. Okay, here's what I can share with you today on performance. The graph at the top shows core level performance of popular floating point, integer, and commercial benchmarks. From the graph, you can see that Power 7, with its smaller core, provides continued performance improvement from Power 6 at reduced frequencies. This is accomplished by first shortening the execution pipelines by taking the high-frequency Power 6 pipelines and establishing new latch points with more FO4 between stages to optimize the pipes for best performance per watt. Second, we reduce the L1 cache latency from 4 cycles to 2 cycles, providing better performance for dependent operations. Third, as I mentioned, we brought the L2 cache closer to the core. This reduces the L1 miss penalties to as little as 8 cycles. I've also mentioned we've expanded some execution units like the floating point unit. We are now capable of doing 4 double precision ops per cycle, and made others more flexible like the load store unit also being capable of doing fixed point instructions. We've also increased the utilization of the pipes by adding 4-way simultaneous multi-threading and aggressive out-of-order execution. The net is a higher performance, more energy efficient core. From a chip perspective, you can clearly see the advantages of a balanced 8-core design. With advances in interconnect technology, cache hierarchy, and memory bandwidth, Power 7 provides greater than 4x performance growth from Power 6 at equivalent chip power. To realize the 4x chip performance capability at system level, additional memory or disks may be needed depending on the workload. Okay, let's switch gears over to energy management. The graph at the upper right shows kind of the classic power management trade-off of wake-up latency versus energy reduction for architected idle modes. The Power 7 architecture defines 4 idle modes: doze, nap, sleep, and Rip Van Winkle, which is associated with power gating. Power 7 chose to implement 2 knee of the curve design points. To optimize for best wake-up time, we implemented nap mode. In nap mode, clocks are turned off to the execution units and frequency is reduced, but caches and TLBs remain coherent to reduce wake-up time. For optimal power reduction at the expense of some wake-up latency, Power 7 implemented a sleep function. Sleep provides almost all the power reduction of power gating, but eliminates the wake-up penalty of reinitializing the configuration registers. In sleep, we purge the caches, then turn off all the clocks. This allows us to drop the voltage below Vmin, or the minimum operating voltage, to a voltage we call V retention. At V retention, the 45 nanometer CMOS chip has almost no leakage current, but still retains state when we ramp up the voltage back up and turn on the clocks. Power 7 supports a variety of adaptive power management features to provide excellent scaling of power with workload. First, for a good starting point at 100% utilization, the chip FO4 is tuned for the optimal performance per watt. Then, to provide a nice steep takedown curve, Power 7 supports dynamic voltage and frequency slewing. This is enabled by a small off-chip microprocessor that is built into all Power 7 systems. The microprocessor monitors several on-chip counters to measure utilization of the system and varies both the voltage and frequency of the chip to provide a square takedown power curve. We continue then until we reach voltage minimum, at which point we continue with a linear takedown curve scaling chip frequency. Power 7 also offers a turbo mode of operation. If selected, this allows the chip to boost frequency up to 10%, leveraging excess power capacity from either non-worst case workloads or excess capacity from unused cores, which may be in an idle or reduced execution mode. Balancing energy between the processor and memory is accomplished by a power proxy. The power proxy calculates the relative power using a set of weighted event counters. The weight assigns energy values for various events like cache misses, floating point ops, memory accesses, etc. The off-chip micro then determines how to optimize performance per watt by shifting allotted power between the processor and memory. Power capping is also supported to enforce a hard ceiling on power if desired. Power 7 continues to provide high reliability and availability features to our customers. New to Power 7 is our 64-byte ECC algorithm in memory. This new ECC algorithm from IBM Research allows a full 8-bit device kill to be corrected on the fly. The memory buffer chip used in Power 7 has also added the capability to support a spare device. In the event of a device fail, the memory controller can transfer corrected data to the spare device with no impact to the customer. Combining the new 64-byte ECC with a spare device provides protection against double device kills on a by-8 DDR3 memory. Another feature in Power 7 is selective memory mirroring. In Power 7, we split the memory channels by pairs. This enables us to selectively pick address ranges to be mirrored in both channel pairs. Mirroring can be used to protect our shared hypervisor against full DIMM kills. Customers may also choose to use mirroring on a per partition basis to protect critical work. Power 7 offers all the RAFS features of previous generations, such as core recovery, sparing, hot node add and repair, and redundant oscillators. The new on-chip EDRAM continues IBM's tradition of high reliability, providing ECC on all data to protect against soft errors. Spare rows, columns, and a line delete feature are available to deal with hard errors. In summary, Power 7 continues the tradition of innovation in the power system processors. This 7th generation chip adds balanced multi-core design, embedded DRAM technology, and 4-way simultaneous multi-threading to the power innovation portfolio, providing over 4 times the performance in the same power envelope as the previous generation chip. The balanced design allows the chip to scale from single socket blades to 32 socket 1024 thread high-end systems. Power 7 is the building block for the clustered petascale PERCS and NCSA Blue Waters project. We received our first chips in the lab at the end of 2008. Pictured at the top right is one of our entry system cards. In this single memory controller configuration, you can see the 8 DIMM slots at the right and the processor hiding underneath the copper heatsink on the left. The 4 buffer chips are located between the processor and memory, and the DIMMs and the SMP connector at the bottom. Currently, we have over 300 systems running in our labs. All 3 operating systems, AIX, Linux, and iSeries, are operational and running in multiple system configurations. Power 7's system general availability will start next year. Thank you.
Do you have any questions and your name and affiliation?
Hi, Rich Gooden. Do you have any idea what your soft error rate is for your embedded DRAM?
Yes, we do, and we're not disclosing it. It's really not that bad. I mean, it's actually about the same as SRAMs. I mean, it's really not that terrible. They're pretty large, deep trench devices. But I can't disclose that, you know that. Another question?
Roger Drawing, CSU East Bay. How many clock cycles does your EDRAM take to access?
Again, I'm a little bit hesitant to disclose that. It's about 1/6 the amount of time it takes to get to main store, so it provides a pretty significant advantage. Bill will be giving you a little bit more details on that in the next pitch.
Todd Besnick, no affiliation. Hopefully this is something that you can let us know. How many instructions can be in flight on a single core at once?
We've almost stopped counting that because it's gotten to be such a large number. On a single core with the 4-way multi-threading, if you go all the way from prefetch to the end of the pipe, it's well in excess of 200 instructions.
From dispatch to the end of the pipe.
From dispatch to the end of the pipe, well, dispatch to completion will be about 100 and 120 instructions in kind of the middle part of the pipe. But then we also have the stuff that's pending, that's getting sent out to for stores and so forth.
Sure. That just gives me an idea of the out of order.
Yeah. I mean, it's a large instruction window we're dealing with. That, doesn't seem to be limiting performance.
Ruby Lee, Princeton University. Could you say a little bit more about this distributed recovery you mentioned, and also how you do the memory scrubbing?
Okay.
What and when do you do memory scrubbing?
Okay. Well, the distributed recovery basically is just taking advantage of the out-of-order execution, so that, say, for example, we detect an error in one of the register files or whatever. What we do is we'll just pretend like it's a branch mispredict. Branch, go back to the point before the error was introduced, and then re-execute. If it's a soft error, it's basically gone. If it's a hard error, what we'll do then is, like I mentioned, I kind of went through it kind of quick. We have core sparing. We can actually transfer the work from that core that took a hard error to a spare core if one's available. And then you asked about scrubbing.
Yes.
Scrubbing is a common hardware technique where we periodically just go through the ranks of memory. We do reads to them. If we detect any ECC errors, we'll just scrub out single-bit errors if we see an ECC error, we'll write the corrected data back. The idea being that as time accumulates, you don't want to be accumulating, correctable errors to the point where you get an uncorrectable error.
So you don't do scrubbing, for example, for security reasons, just for reliability?
When I was speaking of scrubbing, that was basically just to clean up soft errors that may be in the DIMMs.
Mariama from Fujitsu. I have two questions. One is you have mentioned that you have increased the number of the floating point unit to 4 FMA.
Right, we're able to do 4 double precision floating point instructions per cycle.
Are you increasing the number of the architecture registers?
Yes, we are actually. I didn't, again, due to shortness of time here. In Power 7, we went to version 2.06 of the Power architecture, which basically what we did is we merged the vector instructions in the floating point instructions in a backward compatible way. You could do a whole talk on that. The idea being is that you have one set of 64 128-bit registers, then we map the traditional scalar registers and the old VSX registers on that. I believe that should be publicly available, that version 206 is, again, a whole section on it.
And you're supporting the 4-way SMT, and can I say that each thread has this kind of 64 by 128-bit architecture registers?
Yeah, that's correct.
So it's symmetric.
Right, yeah, it's symmetric, yeah. The full architected state is supported by all 4 threads.
Okay. And the next question maybe is, I'm not sure that it is allowed to answer, but can you mention about the power consumption value about the Power 7 chip?
I missed that question.
Oh, what's the power consumption of the Power 7 chip?
The per core what?
Power consumption.
Oh, well, I could have just told you I can't answer that. But I'll go out a little bit further. Basically, on Power 7, this is an upgrade path from our Power 6. So depending on the system, whether it's a high-end, mid-range, or entry system, we go into the same exact power envelope as our previous Power 6 chip and still provide the performance increase.
Got it. Thank you very much.
Okay.
Eric Sedlow, Oracle. You mentioned the vector registers. Are there any plans to extend the vector instruction set or extend the vector width?
Yeah, well, we did extend the vector instruction set so that that you have direct capability for those, all 64 vector registers are directly accessible with the new vector instruction set. There was, I believe, 67 instructions added in version 2.06 of the architecture to give you direct access to those, plus cleverly designing the architecture so they're fully backward compatible. So again, that's kind of a whole talk in itself. I know we got my colleague here. Maybe we'll do one more.
And that's it.
David Cantor. So I'm wondering how many entries do you have collectively in TLBs, particularly relative to the size of the last level cache? It seems like covering 32 megabytes with 4 or 8K pages could require some really large structures.
Well, I mean, I think they're two kind of pretty totally different subjects. I mean, the 32 megabytes of L3 is just a cache into your main store. The TLBs are really when you design TLBs, you want a subset of how much memory you actually provide in the system. I'm not going to share the exact number of TLBs, but I'll make this comment that the number of TLBs, we've substantially reduced the pressure on that by directly supporting large pages. Up till about Power 4, we were strictly 4K page sizes. Now we support 64K 1 meg and 16 meg pages, so that if anybody's running into TLB pressure, they should switch over to larger pages, and that'll eliminate it basically.
So that's your approach to making sure that
you
have to go grab page table entries from memory before hitting the cache.
Pardon? Oh, for fetching TLB page entries? Right. Maybe I didn't understand the question.
Never mind.
Okay, sorry. Catch me offline and we can discuss more.
Thank the speaker. So now we're going to have William Starke. He's also working on the Power 7 processor. He's the chief architect for the memory subsystem in charge of the caches, I/O, coherence. He held a similar position with the IBM Power 6, and he's a very prolific patent writer with over 100 patents.
Thank you, Jose. Okay, before I start, I just wanted to correct one thing. I think when Ron said 6x, he was describing the L3 latency improvement over the previous generation L3, but I think I heard the word memory latency get used. It's roughly a 15x relative to memory latency for whoever that was that asked that question. And you'll be seeing that in a few charts here. Basically, so Ron took you through what is the chip here. But of course, building really great chips, I mean, we've heard some neat stories about multi-core over the past few days. But a great chip isn't anything unless you can put it in a system that really scales well and is robust. And that's one thing at IBM with our P-Series, our customers really value the robust scalability that we can provide. So in order to go from a dual-core prior generation, really our prior 3 generations, 4, 5, and 6 were dual-core, to an 8-core was a massive discontinuity for us. And as Ron touched on a few of those issues, we really felt it was valuable to share some of the insights in how we had to approach taking that forward, not just throwing more cores on the silicon because you can, but taking it forward and basically matching. Because essentially what you have, as you take the compute throughput up by greater than a factor of 4, the difficulty, as many of our speakers in the last couple of days touched on, is actually feeding the beast. And when I'm talking 8 cores here, I'm not talking some kind of small cores where, yeah, we'll just put more of them on and get some throughput. These are cores that, by themselves, if you built a single core design, you would have a very powerful computer. So taking 8 of those really big hungry mouths and feeding them, we really need to figure out how to cheat and beat the physics, or maybe as my boss said last night, we need to find some trickery that helps us out here because Moore's Law doesn't quite do the job for us. So stepping back, once again, I said the systems are really the important thing. It's not the chips. I know this is a conference about chips, but the systems If you look at a traditional, what I'll call a small entry server platform, I know to a lot of people that probably seems like a big entry server platform, but take like a 4-socket dual core type design. We are seeing this trend that the technology shrink enables us to take this into a much higher space, you know, building 16, even 32-way kind of servers. And it almost starts to look similar to the kind of servers we and IBM have been building in the last several generations through Power 4, Power 5, Power 6. We've been building these large, you know, 32 to 64-way servers. It's just that they're spread out across 32 chips. So in one sense, the know-how that you need to be able to take that scalability up to those large numbers of cores, it doesn't really matter how many chips you're putting on, but it is a very daunting challenge. Is it, you know, a simple matter of, you know, yesterday's dual core 4-socket thing, we'll just throw 8 cores on there and, you know, somehow get lucky and it works really well? Well, you know, obviously it's not that simple. And so I'm going to take you through some of the key elements, kind of hitting high-level themes. I apologize, there's not a whole lot we can say in 20 minutes. But just to share, and then I invite you to kind of compare and contrast that, because you've heard some of these points in a few of the other talks. So I think we're all smart engineers. We all kind of have a feeling of some of the elements that we need, but we're gonna be hitting quite a number of them here. Now, obviously, in addition to just taking 4-socket dual core things up to 4-socket 8-core things, the same kind of demands on systems going from single image kind of small servers up to highly virtualized consolidation platforms, that's going to really drive that entry space, and it's going to take off. It's going to need to grow the N-way. But we're also going to be seeing that even with the traditional high-end server. So the 32-socket space, just because we go from 2 cores to 8 cores on a chip, doesn't mean we can cut that back down to some 4 or 8-socket space. We need to take those systems up so that they can grow and provide the kind of value that we see as the IT industry, you know, really goes into the cloud era here. Because the SMP as a structure for building very large systems is the best and most straightforward and robust way to deliver really world-class, virtualized, ultra-scale cloud type environments. So, okay, enough of the system talk. I know we're all chip people. I'll get back to the chip. So how do we attack this? The first is through evolution in the cache hierarchy. We really need to hit it with the technology and with innovation. So if I look at, say, one of our traditional servers, I've kind of abstracted it out. We take roughly 2 megabytes to 4 megabytes of tightly coupled cache per core. And then in addition to that, we need a really big, call it bigger than 30 megabyte tank. Now for Power 4, Power 5, and Power 6, we built that tank with a separate chip that was basically a big pile of DRAM. But you know, DRAM is a different kind of process technology. It doesn't necessarily work and play well traditionally with putting on high-speed, high-frequency processor chips. Now the difficulty, though, as you go from Power 6 to Power 7, you might say, well, why don't I just throw another one of those tanks out there? Well, you really run into some bandwidth issues, because I would essentially have to take the large number of pins coming off the Power 6 chip to talk to the big cache tank chip, and I would need to multiply by somewhere in the neighborhood of a factor of 4. Well, you know, we're really good at, and I think we have a reputation, we throw an awful lot of pins at these things, but that's even a little extreme for something IBM's going to do in this space. So we need to tackle that one. And as Ron alluded to, we really saw the time coming, and we needed to take our fab technology and, you know, going beyond the sort of the conventional, you know, memory DIMM technology that, you know, everybody has memory in their DRAM memory in their DIMMs, and everybody has different speed grades of SRAM. They build really super fast SRAM for their small caches, and they build kind of as big and slow as they can get for their multi-megabyte on-chip caches. We, as I said, had another bullet in our gun over the past several generations, which was this embedded DRAM capability, which it's a DRAM that's a lot faster than conventional memory technology. Still bringing a lot of the density and power value of DRAM, though. And now with Power 7, we have invented the way to mix all the secret sauces together and on the same chip, put basically the deep trench, put the different process steps in there, and not take down that super duper high frequency logic device performance. And so what does that give us? As you saw in Ron's presentation, we're able to take a large amount of the chip, but not nearly as large as it would have had to been, and we can throw a 32 megabyte cache tank out there. And in addition to that, that's not all the DRAM. You also have some really high speed, high bandwidth interconnect on there. I know a few folks were talking in a little more detail about their interconnect. I was just kind of treating that as a business as usual here, but I'll just throw out a number. That interconnect inside there is roughly north of 500 gigabytes per second of internal chip bandwidth. That's connecting all those 8 cores together, connecting them with the off-chip links, the I/O subsystem, and the memory controllers. Now, so we have that big DRAM thing. That looks like it satisfies that bottom requirement of that large shared 30 megabyte plus tank. But then what do we do to solve that 2 to 4 megabyte issue? We need something tighter, faster, but still pretty big. Well, so we use that technology, but now we had to add some microarchitecture trickery to this. And we essentially built that cache so it behaves as 2 different cache levels. We like to call it a fluid cache. So essentially, any of those cores can get to any of that data in that cache, and they can take their working sets around there, and you're going to have various private data, shared data. And basically, that cache is going to come in with a latency component that's roughly 1/3 of memory latency. But then what we do is each core has a fast, local, private region of that cache, and we automatically migrate data to gravitate toward the core that wants it, effectively getting another 5x latency reduction. So roughly you're talking a factor of 15x now faster than local memory. So I think the earlier question on the DRAM latency was really probably focused in this 2 to 4 meg space. How do we look relative to the SRAM we would use in the previous generation? We actually come out extremely close to that latency. It's, actually in terms of number of processor clocks, you're roughly on par. Now, another interesting thing, in addition, we clone data within this cache if we need to, because multiple cores might want shared data and they want it at their nice fast latency. So you don't have to just have it in one place. We can keep it in multiple places in the same cache. Obviously, also, it's a shared cache, so one core or some subset of the cores can get access to the entire cache capacity for their own use, assuming the other cores are either lightly using it or maybe they're powered down and not using it at all. So the fast local L3 region here, if you look at the die photo, I picked out one of the 8, and you can kind of see the pattern there. You can probably kind of figure out which of those macros are the DRAM macros. But that's basically how you can get very quickly to your local up to 4 meg. Now, is DRAM the complete magic thing and we don't need SRAM anymore? No, of course not. You still need the super duper high speed, high bandwidth, ultra low latency you can get in your tighter caches. So we weren't going to take this DRAM as some kind of one size fits all and just say, okay, that's it. So what we do is we take what I'll call more of a higher speed, think of it as a core style SRAM, and Ron mentioned that, and we like to call this the turbo cache. It's basically a 256K, extremely tight, as Ron said, roughly 8 processor clocks load to use. That's faster than we've typically built in our L2 caches before, and it's because we've made it small and tight and private, and it acts as almost like a nice turbocharger. You get that latency, and it's a wonderful bandwidth sponge, for the store-through protocol so that you're not shoving traffic all the way out to the bigger L3 tank, basically giving us another layer in our cache hierarchy. And so you saw the L2 cache next to a core before. Here's what it looks like in the whole big scheme of the thing on the chip. Okay, this was a summary. I'm not really going to talk to it. It's mainly for the printed material, just a nice quick reference for anybody who's curious. Okay, so that's just one bullet in the gun. You need that big cache tank. And 32 megabytes, you don't really want to be smaller than that. The next step, though, is advances in memory subsystem. You're still going to generate a lot of cache miss traffic. You still got all these mouths to feed, and a lot of them are going to need to come from memory. Typically, we would say you're going to need 10 to 20 gigabytes per second of sustained memory bandwidth per core. Now, we hold ourselves to some high standards for memory-intensive stuff because that's been one of our areas that we focus on. Also, you need a lot of memory per core. We need 16 to 32 gigabytes of memory per core. And you're trying to jam all this stuff into a box that has a set of really nasty energy constraints because volumetrically this stuff is just getting harder and harder all the time. So we really were looking to grow the bandwidth, in the ballpark of 4x at the socket level and the capacity as well. So we attack this with a multifaceted solution. We have dual integrated DDR3 controllers on the chip. We focused, because of just the bandwidth to get off the controllers, we put a significant focus in scheduling. We put a large 16 kilobyte scheduling window. That means all the lines where we're currently doing reads and writes to memory, we can have about 16K of those lines swimming around being reordered to optimize their scheduling to the DIMM spec in terms of what rank, bank, all that stuff that you go to, all the timings you got to meet. We also have some energy management, RAS features that Ron mentioned, and we have some sparse access acceleration. I'm not going to go into that too much, but for the Blue Waters program, the massive petascale cluster, there's some key requirements in there where we have a number of neat little items that are baked into this chip and these cores and the memory subsystem. Then we take it out with 8 high-speed 6.4 gigahertz channels. We're using a new differential signaling technology. If you're familiar with our past stuff, we've been taking single-ended and running it really hard. We're still doing it in this program, but we see there's value in the optimized single-ended as well as value in the optimized differential. So we picked the right one for the right job. We felt for memory, the differential was the right one. And with that, as Ron said, we can hit in excess of 100 gigabytes per second sustained per socket, and actually that's per chip. As Ron pointed out, we have a 4-chip socket in one of our configurations that has in excess of 400 gigabytes per second. We have a brand new from the ground up memory buffer chip design that really is built to fit hand in glove with that on-chip memory controller. Each one is like one is one half of the brain, the other is the other half of the brain. You don't have one without the other. A key element here is we have 2 ports coming off the back of this, and that's really what's driving the additional capacity support. And of course, DDR3 DRAMs themselves we support in the 800, 1066, 1333, and 1600 speed grades. The memory controllers live right there. Obviously, everything along the chip edge is off-chip signaling. I'll just mention that briefly. I'm going to be highlighting everything. Everything around that chip perimeter is completely brick-walled with off-chip signaling to a 9-deep level. And into that topic, off-chip signaling technology, really just wanted to focus with you on a few of the speeds and feeds and some changes. I put off-chip cache up here because that was always a huge component for us. But now, as we said earlier, we brought that whole L3 cache on chip. We don't have to devote a massive amount of bandwidth to that. Where do we take that bandwidth? We allocated it to primarily to the memory channels and the I/O bridge and somewhat to the SMP interconnect. So the memory channels, as I said, are better than 100 sustained. well, they're around 180 in terms of raw pin bandwidth. And that's the one thing I want to, as a qualifier, these are raw pin bandwidths coming off. But as a total, we get in excess of 590 gigabytes per second of raw pin bandwidth in terms of real logical functional ones and zeros signals going in and out of this socket. And that's a key ingredient of what you need to feed these cores and let these cores talk to each other in a large 32-socket SMP system, or even in a smaller 4-socket SMP system. You need a lot of this bandwidth. Okay, the last major item here that I want to hit is we really had to exploit the long-term multi-generational investment that we have placed into our coherence protocol. It's something we don't talk about a lot of times, but we wanted to really hit it this time because it becomes a key with this inflection point. So right there you see the off-chip drivers and receivers. Now these are single-ended that are devoted to what we call our local SMP links and our remote SMP links, as well as our I/O subsystem bridge chip connect. Now we take basically that one Power 7 chip, and let's see if the clicker, there the clicker works. And we drop that in, and that is our 32-socket topology. Now, in some talks, we hear about these great capabilities to configure any topology you could ever dream up. We actually leverage the fact that we are our only system house. We have one customer, and it's ourselves. We work very closely with our system team so that we can highly optimize our chips to support specific topologies. And we essentially eliminate a significant amount of tracking logic because of what we can do with the distributed resolution and broadcast protocol. And I'll get into this right here, but first I want to talk about the base. We have a fundamental value proposition in our underlying storage architecture as opposed to some what are traditionally called strongly ordered storage architectures where you really have to worry about, even for threads that aren't interacting at all, you have to worry about they have some defined ordering of updates to storage. The nice thing about the Power architecture is it allows us to essentially have a huge reorder window of allowing updates to kind of drift out to storage as long as we're not talking about serialization conditions. And we leverage that to the hilt. We actually have in a 32-way system, we can have 20,000 simultaneous coherent storage operations all streaming around and getting reordered with each other. We haven't typically talked about this a lot, but going all the way back Power 4, Power 5, Power 6, this is a key ingredient to why we can scale as robustly as we do in these very large configurations. And just as a reference point, the 20,000 is 4x what we had on Power 6, which in its day was a mammoth, unheard of number as well. In addition to that ability to reorder, we really play to it with our implementation in two ways. One of them, and I kind of apologize, I saw some people with charts and they talked a little bit about the way their coherence messages flow and gave a little more of a deep dive. I'm not going to have time to do that. But essentially, unlike most of these kinds of designs where everything kind of has to go to the memory controller to get the final permission, we have a dynamically migrating coherence resolution. It can be any cache anywhere in the system can take on that role, and it's always dynamically shifting around, which avoids sending coherence messages always through a long network of things to find their memory controller. Another thing we do is we have a broadcast-based protocol which is non-blocking, so that we can essentially use pipelining and we use time to do a lot of our tracking. We have a guaranteed arrival window, so there is a bounded amount of queuing, and so we can essentially have messages that get sent, and we have a guarantee that they're going to be seen within a certain time window, and we leverage that to throw out tons and tons of transistors that we would have been using to track those operations. And this is not new. We've been doing this since Power 4, Power 4, Power 5, Power 6, Power 7. Now, what is new is the real challenge that you hit when you put so much here. That system broadcast, as your compute throughput goes way up, is still so high. And actually, our global coherence throughput, our ability to snoop traffic, we had 320 gigabytes per second in Power 6. That's really a lot of global coherence bandwidth. And we managed to jack it up to about 450 gigabytes per second in Power 7. But that's obviously not keeping up with the compute throughput. So what that basically says is when you do these global broadcasts, that's about what you're going to be able to get to. Now we noticed that already though back in 2003 actually, before we were even doing Power 6, we said that roughly around the end of the decade we're going to hit this wall. And so we developed a dual scope broadcast protocol, very similar to the probe filtering that we heard about earlier, except that we embedded it completely in our cache states. We have 13 cache states, not the 4 typical ones or 5 typical ones, but 13 cache states. And we have an integrated scope indicator that lives with every cache line in memory. Now, you may ask, are you adding a bit to every cache line? Well, actually, it's kind of nice. It gets buried in with the error correction codes, and we kind of get it for free. And so what this enables us to do is we can essentially do speculative nodal broadcasts, effectively multiplying the effective coherence throughput by a huge amount. So this provided a lot of value for Power 6. You might have heard one of my colleagues, Jeff Stukley, was here a few years back, and he talked about it. It reduces latency, and it gives us near perfect scaling for memory-intensive workloads, and enabled some ultra-dense packaging. Our 575 compute cluster system really exploits this capability. But for Power 7, this is just an absolute necessity. If we really wanted Power 7 to scale exactly equally coherence-wise to Power 6, that 450 gigabytes would need to be 1.6 terabytes per second. Now what we actually get is if we do this at the nodal level, as I've shown in the diagram, you're essentially going to get the weighted average of some full system broadcasts and some nodal. But the theoretical peak, if you're doing all nodalized broadcasts, is we get 3.6 terabytes per second of coherence bandwidth in our largest system. And we can also take that down. We have a configuration. We don't have to go to the 4 chips in a node. We can keep it to a single chip, which would take us to an effective 14.4 terabytes per second of theoretical coherence bandwidth. So I know I'm running a little over time here, so just in summary, I'll go rather quickly. Our conclusion is we did achieve our goals. We have hardware running in the lab. We have big systems running in the lab. So we've achieved that balance that we know our customers demand through these techniques. And also, we feel that given these trends toward multi-core and towards higher levels of consolidation, these things uniquely position us to continue to take advantage of these trends. We have that history of what we've done in our large SMP, and the economics of being able to track 20,000 operations with very low overhead. We can continue to ride that forward. And also, we have a history of high-density packaging that we've seen over the last several generations. Thank you very much. Do we have time for any questions?
Yeah, we have time. Do we have any questions? One question that I have is that I noticed that your slides acknowledge the DARPA PERCS project. And one of the objectives of the DARPA PERCS was to improve productivity. Do you have any specific things for your productivity improvement that you can talk about or not? Or?
There are a number of things I'd love to be able to talk about at this time, and unfortunately I apologize, I can't go into it. I will mention, as I think I highlighted, there are a number of features that went right into the processor chip silicon to facilitate some of that productivity and some of the integrated clustering support. But we'll cover that in more detail at another time. Yes?
Very nice talk.
Thank you.
The one thing I'm wondering about, if you could tell us a little bit about the computational type of applications you see this working on. Well,
we typically sell our servers to, I'm sorry, outside of servers? I think I'd probably get into a very long discussion if we're going into all the kind of marketing segments, but Well, I'm actually not an applications expert, so you'd probably be better off talking to another expert on that. I build storage hierarchies and nests and caches and coherence protocols, and I generally see applications through the lenses of what kind of horrific traffic rates do they throw at me. Yes?
Bill Huffman, Tensilica. One question, your smaller scope, I couldn't tell whether it was 4 chips or 1 chip was the smaller scope, and in particular, the scope bit in memory, does that tell you about 1 chip or about 4 chips?
That is actually a configurable mode in the hardware, so we can do either one.
Okay.
So if it was unclear, it was probably because I was trying to say both at the same time. It's a static mode that we would decide in a system configuration, you know, which one of those two we wanted to support.
At power up, essentially.
Yes.
Jose Briz, University of Zaragoza, Spain. Have you made any meaningful changes to the data prefetching scheme you had in previous Power 5, Power 6?
Yes, Power 7 does bring in a number of prefetching enhancements. You know, if you're familiar with the Power 4, Power 5, Power 6 line, you know, every generation, you know, we've kind of built upon the previous generation. So you're going to see kind of all the same things that you've seen in the past, but we have added some additional capabilities. Part of that is, as you know, our cache hierarchy now has a few more moving parts in it, so you know, some of it goes along with that. There's some additional software prefetching capability as well.
Thank you.
Sure. Yes?
Ruby Lee, Princeton. I thought this was an excellent presentation. It's really nice to see the balance in the software and hardware. Now, you mentioned a couple of times about consolidation and virtual machines and so forth. So is there some special hardware support for fast world switching between virtual machines?
Fast what kind of switching?
Any kind of fast hardware support, ISA or microarchitecture support.
We do have ways of, you know, we have a number of hooks. You know, you're basically asking about the function that a hypervisor is going to carry out. But one of the nice things is, you know, we're one company, so the hypervisor people, you know, we can call them up and they can call us up and talk on the phone. So we do have a number of things that bridge across the hypervisor and the hardware stack, where we have a number of hooks that they can use for, you know, various kinds of quality of service, you know, and various kinds of policy enforcement, which is really what they're presenting to the customer is a menu of policies, and then they, through their code, you know, translate that down to a set of, you know, hardware, you know, things that they can touch that we provide to them that will, you know, provide policy enablement in the hardware. Yes?
Bill Rash, Intel Corporation. You have 2 memory controllers, and each memory controller has the equivalent of 4 DIMMs in parallel on it. With DDR3 DIMMs, that kind of implies a cache line of like 256 bytes to read 8 words consecutively in a DDR3 DIMM and 4 of them. How do you handle sort of the cache line difference given the width of the memories and the way the memories want to be read?
That's a very good question, and I apologize if I wasn't more clear. We do describe them as 2 memory controllers because mainly they live in 2 physical places on the chip. But you should think of it as each memory controller is broken into 2 halves. And so we basically have a cache line mapped across 2 channels. So think of it as the 8 channels are really 4 banks. And then a given cache line would be mapped across 2 channels so that we can use the DDR3, you know, the run of 8, and essentially map 128 bytes, which we do support a 128-byte cache line, unlike many architectures which are supporting 64-byte cache lines. So it maps nicely to the 2 channels.
So you keep the same cache line as Power 6 at 128 bytes?
That is correct.
Mm-hmm. Okay, thank you.
Yes.
Okay, we're down to the end here, and I know it's late and everybody's tired. And so while I could bore you by thanking all our sponsors, Intel, Rambus, NVIDIA, Micromagic, Wortham Associates, BDTI, True Circuits, Power.org, and Circuit Seller, and I could thank all the committee members and all the volunteers that made this thing possible, and I could thank Stanford for the use of the facility and IEEE Computer Society. I'm not going to do that tonight. I'm just going to say a couple things, which is that I would appreciate it if you would fill out the evaluation forms so we can try to improve the conference next year. That would be very helpful for us. And also to tell you that, excuse me, that all the presentations are going to be available on our website under a password in a few days. We'll send you that password by email. And all the keynotes and panel sessions will be put up in video form. We haven't figured out exactly what form that will take, but we'll notify you by email when that happens. And beyond that, I'm going to thank you all for attending Hot Chips and hope to see you next year.